Right, hello. This is our last student presentation of the day, and we'll be closing things off with some work by Aidan Gomez that covers sort of more broadly applicable use cases in deep learning. So Aidan is a doctoral student at the University of Oxford, and he leads a research group called FOR.ai that focuses on a lot of the same sort of values as machine intelligence community, in terms of providing resources and mentorship to students who may be interested in the field. Aidan's research in particular deals with networks and their applications, and he has also worked in the past at Google Brain under the likes of Łukasz Kaiser and Geoffrey Hinton. So with that, I will give it off to Aidan to talk more about targeted dropout. Thanks.
Great, thanks so much. Yeah, so I'm a student at Oxford. This is work that I did back at Google Brain Toronto. And basically the kind of area that we're addressing is sparsification. So it's probably safe to assume you guys know what a neural network is. And there's this feature which is, it's this enormous densely connected network, which it tends to be unnecessarily dense. What we find is that at the end of training, you can usually remove large segments of this network without hurting the performance too much. And so what we'd like to see is we'd like to come up with principled methods to inform that pruning, to inform which subnetworks are really the important ones. And so that's what I'm trying to make easier. So yeah, like I said, the network is this big, densely connected graph. And so if we were to just naively try every single subnetwork, it's kind of infeasible since there's a combinatorial explosion as we get deeper and bigger networks. The kind of current state-of-the-art networks exist on the order of millions, or now we're entering a phase of billions of parameters. And so considering all those subnetworks really isn't feasible anymore. We need to come up with smarter techniques. And so in order to do this, we need to be able to say, okay, this particular subnetwork is important versus this one which is not important. There's going to be some subnetworks which really dictate the function that we've learned. And so this is kind of important for things like mobile applications where it's difficult to adopt these state-of-the-art techniques since they're so expensive. They require specialized hardware to compute. And so if we could just take these enormous deep networks with millions or billions of parameters, strip them down to just the minimal fundamental function or the minimal function that they've learned, that they've been optimized towards, that would be fantastic because we'd see greater adoption, which is what all of us researching in this community really want. We want to see neural networks applied to almost everything and usable almost everywhere. Okay, so I have a few equations in here. I'm going to try to breeze through them and just give you a high-level intuition. So what we're looking at here is the change in a loss function after deleting some subnetwork. And so this is what I mean by importance. We want to ask, how much does it hurt us to remove this subnetwork from the network as a whole? How much does our loss increase? And so if we were to just go through every single subgraph in our neural network and say, okay, how much did it change this one? How much did it change this one? It would take, on the orders of years because there's so many subnetworks. So we have to start by making some simplifying assumptions. And the very first one we can make is a second-order Taylor approximation. And so that's what I'm doing here. I'm saying that this loss is approximately equal to some function of the gradient and the Hessian, as well as that network which we're considering deleting. And that's going to be our judge of importance. So yeah, the theta is the network parameters, D is the deletion vector, and H is the Hessian. So now instead of having to do a forward pass for every single subnetwork that we're considering, and the forward passes, they're composed of all these vector matrix multiplications and nonlinearities, and those are quite expensive to compute. Now what we really need to focus on is only this middle term. And so why only that middle term? So this first term, it's going to vanish. That's exactly what we're optimizing. So we're trying to find a point in the loss function where we reach a minima, a critical point, where that gradient goes to 0. So we don't really care about that first term. The third term we just call error, and we just kind of ignore it. The second term is really where we want to focus. And so the Hessian is is great. It makes things a little bit simpler, but it's also intractable because the Hessian is going to be number of parameters by number of parameters in size, which is, again, computationally intractable if we have billions or hundreds of millions of parameters. We just can't compute that. So the Hessian ends up being enormous. So we need to go further. So we started off with just a change in loss, which is quite expensive to compute. We went to a second order approximation where we only really need to consider vector matrix multiplications. So it cheapened things a bit, but not enough. And so another assumption that we could make is to strip down that Hessian, to sparsify that Hessian. So it's this enormous million by million matrix. And so what Jan LeCun did back in 1990 in a work he called Optimal Brain Damage is he made this assumption where the Hessian is just a diagonal, zeros everywhere else. So we can throw away a massive portion of this matrix and just consider the elements equal to the number of parameters along the diagonal. And that cheapens things a lot, but that's a big assumption to make. And so it's also still expensive. So getting those second derivatives is still perhaps a little bit too much to do. It's kind of a pain. So we could go further and we could say, all right, well, instead of considering the Hessian, let's just ignore the Hessian and look at that first term. And so I told you that first term vanishes, but in practice it actually doesn't. So while the expectation of that term should vanish, some Molchanov and colleagues, they suggest that the expectation of the absolute value is still informative. It gives us the variance of that quantity, which is something like the sensitivity of the function back to those parameters. So it's kind of useful. But again, I think this is a little bit too complicated. I don't want to have to code getting the gradient and making decisions off of that. So I want to go even further. So we went from a second order approximation to a first order approximation, but I want to go to a 0th order approximation. And so this has existed forever. I think Jan LeCun mentions it in personal communication with Rumelhart back in 1988. And this is like the craziest assumption you can make. It seems the furthest you could possibly go from the truth, and yet in practice, it works quite well. But obviously, it's still far from perfect. And so I came up with this kind of visualization tool, which I think is really useful for seeing dependence of the function on particular weights. And I'm going to skip over all of this stuff. Basically, the idea is we're going to focus in on this second term to visualize how this function depends on different weights and how weights depend on each other. And so the principal idea is that you want to order the weights so that they're decreasing in magnitude. And so in the top left corner, you have your largest weights, the highest magnitude weights. And as you extend outwards, you have smaller weights. So if I go to this picture. So up here, we have our largest weights. And then as we go to the outsides, we get smaller and smaller weights. And the assumption that we're making is a 0th order assumption. So we're going to judge the importance of parameters based on their magnitude. We're going to say that big parameters are extremely important and small parameters are not. And so the impact on our loss function is actually going to be the sum of the values in this matrix of a square in the bottom right corner. And so you see inside this square, there's some dark values where there's impact. There's impact to our function by deleting these parameters. So what I'm showing here is we have small parameters, which are important to our network. And we don't want that. We want our small parameters to align with our assumptions about what important parameters are. And so we kind of want to clean up this matrix. We want to force all the density, all the importance into that top left corner, which is the part we're going to leave, because we're going to end up deleting what we call unimportant weights, which are those small ones in the bottom right corner. And so the way that I'm going to try to ease this transition is a technique called targeted dropout. And so targeted dropout, it's inspired by Hinton's description of what dropout does. His description goes something like, it reduces coadaptation between units in neural networks, And the way I interpret that is it reduces the dependence of higher neurons on the lower neurons that preceded it. So what Dropout does is it randomly removes units from a network. And so a higher unit can't rely on the presence of a lower unit since it's being stochastically dropped out. And so what it ends up doing is it learns some function that isn't solely dependent on some subnetwork. So the idea with targeted dropout is we augment this. We don't just drop out entire units at random with the same probability. What we do is we consider a particular unit in a neural network. We judge the importance of its incoming connections based on their magnitudes. We rank them, and then we select only the smallest k%, or what we'll assume is the least important k%. And then we apply dropout to these. And so the effect is the subnetwork that isn't being dropped out, that large magnitude subnetwork, learns to be robust to the removal of these dropped out elements. So we're kind of incorporating into training our own assumptions about what importance is. And then after training, hopefully we've learned something that's robust to their removal so that we can just remove them and we'll get something that, performs the exact same computation and it doesn't lose too much accuracy despite having a large proportion of the network removed. So don't read this code, but this is just to give you the idea that this is really simple. This is like something that can fit on a single slide. You can just drop it into your neural network. You don't have to compute Hessians. You don't have to compute gradients. This is purely based on magnitude, and it's incorporated right into the training procedure. So this is something that's incredibly simple. Okay, so I showed you this picture of the unregularized model where we had lots of density down here on our small weights. So these small weights do represent something important to our function. And let's see what happens when we apply targeted dropout. So when we apply targeted dropout, what happens is we clean up the dependence in this network. We kind of force things up into that upper left corner where large magnitude weights are important. They dictate the function that we've learned. And so we have some pretty interesting results which show here I have along the y-axis the sparsity, the degree of sparsity in the neural network. So the number of units or weights that we've removed. And with no regularization, you really start losing things around 70%. But when you apply normal dropout, things get worse. So the network starts depending not on a subnetwork, but the whole network because parts are getting dropped out. And so normal dropout hurts things, but then when we apply targeted dropout, we can really draw down that robustness. And this becomes even more clear when we go to our unit level results. And so here, no regularization performs extremely poorly. Dropout hurts it even further. And then targeted dropout is really capable of drawing down that robustness. And something interesting is that down at something like 50% of our network, we actually are performing better than an unregularized network with full density. So there's perhaps some regularization effect tied to Occam's razor. People have theories about simpler neural networks are better. They generalize better. There's some generalization error bounds that exist. And so maybe this could be used to kind of strip down the complexity of our models. And so the last idea is instead of targeting a fixed proportion throughout training, what if at the beginning of training we started with started with no targeting, we apply no dropout, and then throughout the course we start penalizing the model for relying on smaller magnitude weights? What if we start gradually annealing that targeting proportion up to some quantity that we want to have, some quantity of sparsity that we want to have? So for instance, for sparse operations to be justified, you need a particular degree of sparsity inside your matrix multiplications. And so maybe that degree is something like 80% sparsity, 90% sparsity. So we have a desired target sparsity that we need to reach. And so this really kind of changes the game. So what ends up happening is whereas before we started dying out at 90% sparsity, we started losing our accuracy, now we can really start digging deep and getting down to 99% sparsity and even further. And so kind of what I'm depicting here is we started off with this enormous ResNet, which is something close to state-of-the-art in vision. It's massively over-parameterized, very difficult to get down to something like 99% sparsity. But now we can learn a pretty good function, a function that does really quite well on the test set with only 1% of the network remaining. There's only a single percent, 1/100th of the network remaining, and yet it still learned to represent the data. So there's this really interesting feature of neural networks where clearly they don't need this over-parameterization, but if we had have started out with a neural network that was 1% the size of what it was at the beginning, it never would have trained, it never would have learned this. We know that deeper, larger neural networks perform better. And so this kind of gives us a route to getting down to that small network without having to, do all these complicated sort of hacks and regularization schemes and post hoc routines, which previous literature has relied on. And so in conclusion, I just kind of want to emphasize that we need better sparsity support. And so hardware right now in GPUs, sparsity is as bad as it can be. So I'd love to see in our frameworks more integration for sparsity support for production applications of neural networks. The other really interesting thing that we've noticed is that you can actually do early pruning. And so you don't need to wait your whole training routine before beginning pruning. You can train for, let's say, 10% of time, 10% of your training routine, and then prune and still reach the same accuracy. So we could actually save ourselves as researchers the time of waiting to complete by training a much smaller network for 90% of the time. And the other thing I wanted to mention is I run a group called FOR.ai, which was mentioned when I came up here, and we focus on giving students the opportunity to collaborate with some of the top labs in the world, like Oxford, Google Brain, the Vector Institute in Toronto, and really get some mentorship from some really great figures. And so if that's something that interests you, and if that's something that you want to get into, check us out, and we'd love to have you. Yeah, thanks so much. And if there are any questions, hey.
Hi, thanks for the talk. I had a question. If you're able to prune down to 1% of your original network, is there any way that you could? Because a big problem with neural networks is that they're uninterpretable, right? Since you have so few weights left, is there any way to help with that interpretability, given that you just have less weights to care about?
Yeah. So this has been asked to me a few times how targeted dropout could help with explainability. And it's not something that I think is immediately clear. I'm not sure how much this would help. Like, perhaps if you want to identify which filters are determining a prediction, it's easier if you're pruning filters, because then you have less filters to consider. But the most promising results from targeted dropout were with weight level pruning. And so I'm not sure if it helps all that much, but it's definitely worth the thought. And I'm thinking about it, but haven't really found anything. Yeah.
Thanks.
Thanks so much. All right, thank you guys.